Hello everyone, I'm Hyung from KAIST. I'm going to present my work, CodeTree, a system for learn sourcing subcode hierarchies and code examples. Hierarchical summaries are helpful in many learning scenarios. When you check examples to learn how to build a chair, learn how to write a program, or learn how to make up, hierarchical summaries of the examples can give you an overview and let you navigate information at different details. In programming education specifically, code examples can have the hierarchical summaries. On the right is the hierarchical summary of code example on the left. Lines of code can be grouped into a subgoal that divides code into smaller functional units. Each subgoal comprises of a code group that indicates its mapping to a code and a subgoal label that explains the function of the code group in natural language. A hierarchy of these subgoals is helpful for understanding the code example and learning to transfer the algorithmic structures to novel problem contexts. In this work, we investigated a scalable approach to generate subgoal hierarchies in the context of programming education. Generating quality subgoal hierarchies at scale is challenging. Expert-driven methods are not scalable because there are far fewer experts compared to code examples online, and it is manually intensive to identify subgoals at all levels. There is also a possibility of experts overlooking detailed subgoals that could be useful for novices. Data-driven methods are scalable, but often difficult to generalize to different domains because they require collecting large-scale data for each specific task. Although large language models show notable performance in explaining code, they still struggle to decompose complex content in many domains. To achieve quality and scalability, we looked into learn sourcing. Learn sourcing is a type of cross-sourcing that engages a multitude of learners in pedagogical activities to generate meaningful data for future learners. For example, we can use learn sourcing to find the answer to a math problem. We can ask learners to solve the problem and submit their answers. We can then use majority voting to aggregate submitted answers and identify the most probable answer. Prior research has shown that learn sourcing is scalable, as the pedagogical activity can elicit voluntary participation of learners, and learners can collectively create quality data with appropriate quality control mechanisms in the data aggregation. To apply learn sourcing to quality subgoal hierarchy generation, we set 3 design goals. First, we aim to design data aggregation pipeline that can populate subgoals at as many levels as possible because subgoal hierarchies with more levels can provide finer-grained guidance and feedback. Second, since subgoal hierarchy generation is cognitively demanding, we want to decompose it into microtasks. But at the same time, we have to ensure that each microtask helps learners review a code example as a whole. Lastly, we wanted to support generating and navigating subgoal hierarchies by providing a visualization that maps hierarchies to code examples. Following the 3 design goals, we built CodeTree, a learn sourcing system that generates high-quality subgoal hierarchies while supporting reviewing of code examples. CodeTree provides learners with 2 pedagogical activities. Learners can use CodeTree to enhance their understanding of code examples by either self-explaining the subgoals of the code examples on their own or selecting the best explanations of subgoals for a given subgoal hierarchy. CodeTree collects diverse learner-generated subgoals from Activity 1 as an initial poll, uses a data aggregation algorithm to build a subgoal hierarchy, and leverages learners' votes on subgoal labels from Activity 2 to identify the best subgoal labels. This is the user interface for the 2 pedagogical activities. In the first activity, namely the generation task, learners self-explain subgoals of the code examples by grouping code lines into functionally meaningful units and describing each unit. Learners can check the lines to group on the right and write down explanations on the left. In the second activity, the selection task, learners solve multiple choice questions that ask them to select the best explanation of the subgoal for each code segment. Learners can also add their options if they have a better explanation. Now I'll explain how we designed CodeTree to follow the 3 design goals. To populate many levels of subgoals, we designed a hierarchy generation algorithm that prioritizes subgoals with more sub-subgoals while skipping the subgoals that conflict with pre-edited subgoals. For example, there are subgoals submitted by 3 learners. The algorithm first calculates the priority of each subgoal, which is the number of other subgoals that it contains as a subset. There could be a conflict when adding a subgoal to an existing hierarchy when code groups partially overlap. By prioritizing subgoals with more sub-subgoals, the algorithm populates subgoals at multiple levels. To balance the task load and integrity of learning, we divided the hierarchy generation task into 2 microtasks. Among many ways to divide the hierarchy generation task, we designed these 2 tasks to help learners review the entire code, following the subgoal learning activity design from previous research. For instance, we could have asked learners to identify the subgoals of a small segment of code at all levels, but we thought it would go against learners' needs and motivation to review the entire code. To visualize the overview of subgoal hierarchies and the mapping between code and subgoals, we developed this color bar visualization. Color bar visualization is applied to both pedagogical activities. Each color bar besides code examples represents a code group. The vertical position of a bar indicates the group of code lines that go together. Through a user study, we explored the following 3 research questions. We evaluated if CodeTree can learn source correct and comprehensive subgoal hierarchies at scale, if learners find the 2 pedagogical tasks helpful for learning and manageable to do, and how the color bar visualization helps learners understand and generate subgoal hierarchies. In our study, participants were 45 college students who took an introductory Python programming class only. We filtered those who scored perfectly on our pre-test and compensated participants with $17 for a 90-minute session. The participants were asked to learn the usage of while loops in Python by reviewing 3 code examples and solving practice problems. Participants were randomly assigned to one of 3 conditions. In the baseline condition, participants reviewed 3 code examples by passively rating them. In the generate and selection task, learners actively reviewed the same code examples through the generation task and the selection task, respectively. We conducted all sessions with generate participants before any select participants to populate subgoal hierarchies for the selection task. This was the study procedure. Participants first took a pre-test comprised of 5 multiple-choice questions about the usage of a while loop in Python. Then, generate and select participants received tutorials about subgoals and interfaces. Baseline participants received knowledge training, which exerts a cognitive load comparable to the subgoal training. Participants reviewed 3 code examples and solved 3 practice problems on the while loop. After that, we measured participants' cognitive load, performance, learning gain, and satisfaction with their learning experience. I will outline the findings from the study. We recruited 2 computer science PhD students with TA experience to evaluate the quality of subgoal hierarchies generated in the study. The quality of code groups and subgoal labels was high. More than 90% of code groups were meaningful, and 80% of subgoal labels described code groups correctly. We confirmed that each participant's performance was high, and this resulted in correct subgoal hierarchies. We also looked into how fast we can create subgoal hierarchies. We ran a simulation where randomly sampled participants performed the generation and selection tasks. The figures show how an increasing number of participants affects the subgoal hierarchy quality in terms of code groups and subgoal labels, respectively. We observed that the quality saturates around 5 learners, indicating that learner sourcing is a scalable approach to generating quality subgoal hierarchies. Our pre and post tests show that generation task had a minimum to large effect on participants' code tracing skills, which is to interpret a given code. Generate and select participants also had higher self-reported levels of understanding of the 3 code examples compared to baseline. Many participants remarked that they could understand code better by decomposing code examples by themselves, and the feedback from the selection task was useful in confirming their understanding. While prior research on subgoal learning also expects improved performance, our work is meaningful as it confirmed the result in the context of learner sourcing. Lastly, we asked the participants to rate the usefulness of the color bar visualization in their tasks. More than half of the generated participants reported that the visualization was very effective and helpful for generating subgoals. On the other hand, select participants gave low ratings because most of them did not notice the visualization on the interface. I'll end my presentation with this discussion. Many of you might have wondered if learner sourcing is valuable in the LM era. I argue that learner sourcing is still valuable. First, there will always be tasks that AI will perform poorly, and learner sourcing can be a viable solution for data collection. Second, learner sourcing can benefit human learning. Finally, future learner sourcing systems can use AI to improve the learning experience and data quality further. I do not think LLMs will replace learner sourcing. Learner sourcing can complement LLMs and vice versa, and it would be worth extending learner sourcing in this new era. Thank you for listening.